Module 5, Session 2. Session 2 will cover the following content. Learning Outcome 2.4.4. Find the equation of the tangent to a graph at a specific point. Learning Outcome 2.4.5. Solve practical problems involving rates of change. Learning Outcome 2.4.4. Find the equation of the tangent to a graph at a specific point. Remember from the previous module that the gradient of the tangent to a curve is the derivative at that point on the function. We can follow these points to find the equation of the tangent to a graph. Step 1. Find the derivative of the function f prime x. Step 2. Substitute the x value of our point into this derivative to find the numerical value of m. Step 3. Substitute m and the coordinates of the point into the equation of a straight line y equals mx plus c, or the gradient point formula y1 minus y2 equals the gradient multiplied by x1 minus x2 to find the equation of the tangent. This should be a straightforward section for students because of its procedural nature. Please work in small groups to do this activity on finding the equation of a tangent to a curve. Nominate one group member to teach this example to the group. Give feedback to the chosen lecturer. Comment on which aspects students find difficult and suggest how to help them. Let's watch a video of the solution.
We have to calculate the equation of the tangent to y equals to 3x squared minus 2x at a particular point 1 and 2. So ladies and gentlemen, the equation of a tangent, so a tangent is a straight line. So the equation is y minus y1 equals to mx minus x1. Brilliant. We don't have the gradient, but we can find the gradient because gradient of a tangent, m of a tangent, is equal to m of f of x at there we go. So what we must find out now, we must find the gradient of this function. And then this gradient, once we found this gradient, we then substitute it. with the value of this point. This will help us a lot. You will see now what I mean. So we know that f prime x is equal to 2 times 3 for this function, x minus 2, which is equal to 2 times 3, 6x minus 2 is equal to f prime x. Now, it is very important that we understand the following. We want to find the gradient at x equals to 1. Because that's where these two functions meet. So let's do that. Six times 1 is 6, minus 2 is 4. Okay, so we have that. Now, you have the gradient now of this function at this point. So as I've said, the gradient of the tangent and the gradient of this function at this point, they are equal. So this particular point being x now. So we know now from the equation that y minus y1 equals to m. M in this case is 4. Open bracket x minus x1. The next thing we need to do, we use the point now. So we use the point. What is that point? This is the point we must use, the one which we were given. 1 and 2. So when you see x, you put 1. When you see y, you put 2. So y is y minus 2 equals to 4 into x minus 1. So what does that give us? It gives us y. We can transpose this to the other side, equals to 4 times x, 4x, 4 times minus 1, minus 4. Transposing this to the other side becomes a plus 2. Finally, y is equal to 4x minus 2. This is the equation of what? This is the equation of the tangent.
Learning outcome 2.4.5. Solve practical problems involving rates of change. In general, a rate of change is the rate at which something increases or decreases over a period of time. You will remember from the previous module that the derivative gives us the slope or gradient of a function at any point. We also learnt that the instantaneous rate of change of a function at a point is the gradient at that point. We can also find a second derivative of a function. This is new to students in level 4. To find the second derivative, we first find the derivative of a function and then find the derivative of that derivative. First and second derivatives are useful for practical examples. For example, velocity tells us how displacement is changing with respect to time, and we need the first derivative to find velocity. Acceleration tells us how fast velocity is changing with respect to time. For this, we need the second derivative. Work in groups for this practical example using rates of change. Nominate one group member to teach each part of this question to the rest of the group. Give feedback to the lecturers and discuss the problems experienced by students and lecturers with this section. Let's work through the solution together. An object is projected vertically upwards against gravity. Its displacement s in meters during a time t in seconds is given by s equals 40t minus 5t squared. Question 1. Calculate the velocity after 2 seconds. From the question, we know that the equation for the displacement is s equals 40t minus 5t squared. Displacement here is a function of time. We can write this as f of t equals 40t minus 5t squared. The first derivative of s gives us velocity, so we find the derivative of f with respect to t is 40 minus 10t. We need the velocity at 2 seconds, so we substitute this into our derivative, which gives us a velocity of 20 meters per second. Question 2. Calculate the acceleration after 2 seconds. To find the acceleration, we need to find the second derivative of displacement with respect to time. From question 1, we know that the first derivative is this. We differentiate again to get the second derivative, which equals negative 10. We need to find the acceleration after 2 seconds, which means our acceleration after 2 seconds is negative 10 meters per second squared. Question 3. Calculate the time taken to reach a maximum height. We know from level 3 that in order to find a maximum, we let the gradient of the curve equal 0. The first derivative of s will give us the gradient. So 40 minus 10t equals 0. We solve and get a time of 4 seconds for the object to reach the maximum height. Question 4. Calculate the maximum height. We have just established that the object reaches the maximum height after 4 seconds. We substitute 4 into our displacement equation and then solve to find that our maximum height is 80 meters. Question 5. Calculate the displacement after 6 seconds. We substitute 6 into our displacement equation. We then solve to find that the displacement after 6 seconds is 60 meters. Question 6. calculate the distance travelled in 6 seconds. We now know that it takes 4 seconds for our object to reach a maximum height of 80 meters. We also now know that after 6 seconds our height is 60 meters. So we can calculate the distance travelled by working out how far the object has gone up plus how far it has come down. This gives us a distance of 80 meters up, our maximum height, plus 20, which is 100 meters travelled in total in 6 seconds. Now let's watch a lecturer work through another rates of change example.
Air is let out of a large round balloon at a rate of 0.4 cubic meters per second. At what rate will the radius decrease if the radius is 3 meters? So imagine a round balloon. Of course, we can look at it as a sphere, in a sphere shape or spherical shape. First of all, what we know is that the volume changes with time. So we have dV dt. So the derivative of the volume with respect to time will then be equal to 0.4 cubic meters per second. This volume is decreasing, so which means that there must be a minus here. The next thing we know that we have an unknown of the derivative of a radius with respect to time. So at what rate will the radius decrease? So we need dr dt. Furthermore, when we do our solution, we're going to focus here. We know that the derivative of radius with respect to time must be equal to the derivative of radius with the volume multiplied by dV dt. So in other words, this will cancel with that. Now we must work such that we get these two factors, so these two derivatives. Now let's find the first one, which is our volume. Our volume is a spherical shape, so we're looking at a sphere. 4 over 3 pi r cubed. That's our formula. Then we must differentiate this. So we're gonna get what? Gonna get dV dr. So we find the derivative of this volume with respect to radius. This is the volume, the derivative with respect to radius. So with respect to r will then be bringing the power down 3 times the coefficient which already exists, 4 over 3. Pi is a constant. R 3 minus 1, 2. We can see that 3 and 3 cancel each other. Therefore, dV dr gives you 4 pi r squared. This is dV dr, but what do we want? We want dr dV. So we want the inverse of this, or the opposite of this. So dV dr dV must be equal to 1 divided by dV dr, which then gives us 1 over 4 pi r squared. So we have found dr dV. This we got. Now we need dV dt. We have dV dt from the given statement. Now let's put them together. 1 over 4 pi r squared, which is this part, multiplied by dV dt minus 0.4. We don't have to worry about the units. What does it give us? It gives us, so we're going to continue with it around here. So it gives us of negative 0.4 times 1, which is negative 0.4 4 all over 4 pi r squared. We have a condition here. What is our condition? R is equal to 3. We've got that condition of a radius being equal to 3 meters. Let's then substitute. We're going to need the aid of our calculator. Minus 0.4 all over 4 pi, open bracket, 3 to the power 2. We need a solution here. Your answer becomes negative not, actually let's write it in the form it is, negative 3.56 times 10 to the power of negative 3, which clearly means that it's not, look at here, not 0.00. So you move your decimal point 1, 2, 3. So you need a 3 here. 5. So your decimal point 1, 2, 3. That's what it means by the power of negative 3. From 3, as the decimal point was originally here, you're going to move to the left. 1, 2, 3. So your decimal point then sits here. So at what rate will the radius decrease? If the radius is 3 meters, the radius will decrease at a rate of 0.0035 meters, because the radius is in meters, because this is derivative of a radius with respect to time, so per second.